Alright, so here we are with a little bit more review. We are now going to be talking about quadratics and their properties. So, first piece here, especially with quadratics, is that quadratics are a polynomial, specifically of degree 2. So, if you're looking at any polynomial function, remember that standard form is listed here, and it's always the greatest power to the least power when you write them in the order they should be in. From this, again, the degree is going to be the largest exponent. And then the leading coefficient is going to be the, what are we going to call it? The multiplier of the variable with the largest exponent. So in this case, the example here has 4 as its largest exponent, and then a as the leading coefficient. Alright, then our next idea here is that polynomial terms have variables which are raised to whole number exponents. So we are never going to be seeing a polynomial that has like an x to the half. That's not a polynomial. That is going to be a function that we can use, but not a polynomial. Or else the terms are just plain numbers. So again, whole numbers, plain numbers. There are no square roots of variables, and if you remember back to Algebra 2, when we did talk about something being x to the half, that's actually the same as the square root of x, because of the power that is a 1 here, and then the square root, which is a 2. Either way, that means that if this first one wasn't allowed, as I just mentioned, then that second one wouldn't be allowed either. So no roots of variables, no fraction powers as we have here, and no variables in the denominator, so we can't be having this. Now again, that can be a function that we will go over later, but it's just not known as a polynomial. So, again, a polynomial is a bunch of terms added together, and so we've got some examples of what is a polynomial. You can do your basics of x squared plus x minus 1, okay? But what is not a polynomial is what we have listed over here as x to the half, square root of x, even cube root of x, and then 1 over x. Alright, this is our standard form of a quadratic function. I mentioned it earlier. The reason that it's quadratic is because we're talking about it being a power of 2. You can also have this, and in Algebra 2, this is when we were having some fun. You can actually write from standard form to the vertex form. Vertex form is more of when it was used when we were talking about any sort of translations or transformations that were happening. We'll go over that in a second, but the idea is that H, for instance, moved it left or right, K moved it up or down, that kind of thing. So there are two forms of your quadratics that we're more likely to see, and that's going to be your standard form and your vertex form. Vertex form is super helpful because literally the vertex of that peak or that trough, depending on what's happening, is going to be h comma k. So whatever the h value is here, technically it's whatever you see and then the opposite because of this negative here, and then the k value here. So very helpful when it's in that format. Also, when it's in this format, it's easy to see how it has shifted as well. All right. The next one, if we are in standard form, to find the vertex and the axis of symmetry, again in the standard form, you would need to take from ax squared plus bx plus c, you would need to take this a from here and this b from here, and make it the opposite of that b over 2 times a. So if you want to find out what your x value of the coordinate is, or your h, you're going to do the negative b of 2 times a. And if you want to find the k value, you're going to plug in whatever you got for your h. So again, your x value is going to be finding that h of the opposite of b divided by 2a, and then plugging in your h will get you the y value of that maximum or minimum. And then your axis of symmetry is actually the same as just your x coordinate of the vertex. So it's just the x equals x coordinate of vertex. Because if you're imagining this parabola, and we know that this is 2, 4, the line of x equals 2 would be the thing that goes through that point and cuts it in half. So again, it's just x equals, in this case, 2, because it's the x coordinate of the vertex. All right. If you put it all together, this is where we were, where I was discussing what h and k end up doing. So as we saw in Algebra 2, if you have this a value or a number way out front of your vertex form, that is going to be the thing that vertically stretches or compresses. So if it is stretching, we're talking about it being a larger number, like 5, okay, but if it's going to compress, then we're going to have a fraction, okay. So after that, if a is negative, so if we have a negative sign out there, it does reflect across the x-axis. It turns out if b is negative, it would reflect across the y-axis, which is not very helpful because it's symmetric on the y-axis usually. So that's not actually going to do any sort of reflection, which is what this piece is. So in that case, part B is a horizontal stretch or compression, and again, based on what the number is. This one is actually opposite of what you might think, and so these two right here work opposite. So for instance, if you see a stretch, that's because B is actually a fraction. And if you see a compression, it's actually because it's a larger value. And then your horizontal movement, as we see here, is opposite. It's going to be left if you're saying that you're adding, which is weird because the left more you go, it seems like the more positive you would go. And then you're going to end up moving, left is usually negative, and then right is going to be positive. And again, if you don't remember what each of these is, you can in fact just take the standard parent function that we did all the graphs of in the parent function worksheet, and you can just graph the original parent function and the function you're examining, and you can just look to see versus know from the formula. So you can always go ahead and get out that grapher. And then K is talking about vertical movement. And again, we did go over this in algebra, so hopefully this is something that you've seen, and now you realize, yes, I probably should remember that, and so that practice will come in our assignment. Or right here. So we're going to describe how to transform the graph of the parent function of every quadratic, which is just x squared, into the graphs of the following through a series of stretches, reflections, all of that good stuff. So both of these are in vertex form, which is nice because they're just going to be the h and the k value. So taking a look at our previous format, we have an a value of 2, an h value which looks like it's going to be positive 3, but remember that this actually comes from x minus something, and so that something is actually negative 3, so my h is negative 3. And then your k is negative 5. So because of that, the vertex becomes negative 3, negative 5. Again, that's why it's quick, because it's in vertex format. And then the axis of symmetry is just going to be x equals negative 3. They also want you to describe what this means. And so this a value here going back to those notes from the previous, is going to be a vertical stretch because it's a 2. So we're going to say vertical stretch. The h, remember, is talking about moving to the left, even though the value in the equation looks like it's saying positive. Because it's a negative here, we're talking about moving left. What color was that? Blue. So we're talking about moving left. And then this bottom one here, the k value is talking about moving down. And of course it is by a factor of this actual number, so we're moving left 3 units, moving down 5 units, and vertically stretching by a factor of 2. Alright, this next one, again, is broken down into these pieces. So our a value is -1/2, which means 2 things will happen. We've got the half, so we're going to do a vertical compression, and then the negative, it's going to flip over the x-axis. So I'll write that. Vertical compression. Oops. And flip over the x-axis. The next value that we have is that it's an h, sorry I wrote b, an h of 2. And so in that case, again, it looks in the equation like it's saying that we would move left 2, but because the h is actually a positive 2, we're going to move right 2. And then our last value of 3 means that the k value is 3, and so we're moving up 3. And so again, our vertex is going to be h comma k, and so it is going to be 2 comma 3. And then the axis of symmetry is going to be x equals that h value, or in this case, 2. Alright, the next piece is going to be a little bit heavy on algebra, but there is going to be one just like this in the assignment, so I wanted to make sure that we could walk through one of them. So, we're supposed to write an equation for a quadratic function whose graph contains the given vertex and point. And so if you remember back to linear equations, it's really nice because linear, you can get 2 points and you can make any line. Well, it turns out that if we are given a vertex, specifically, and any other point on a quadratic, we can in fact get the equation. So, first thing that we're going to do is realize that our equation is going to come from that standard form, but because we are given the vertex, we're going to be writing it in that vertex form of a times, x minus h squared plus k. I keep setting my palm down so it starts writing at the bottom there. Alright, then we look through what we are given. Turns out we're given an h, we're also given a k, and an x and a y. And so if we look at what we have here, we can fill in y, x, h, and k, and so the only piece that we don't have is actually this a value. We did go over it in Algebra 2 that if we had a b value in here, turns out that we could square root and move it out, and it would become an a value. So really, the b value ends up not being used very often, and so we are just looking for that a. So, in that case, if we fill in each of these pieces, our y value is -27, keep the a. Our x value is -4, and we'll subtract the h value, which is -2, have a squared, and then our k value of -5. Now we're going to evaluate and simplify as much as possible. So inside here, lots of things happening, but it's really just -4 plus 2. So we have -27 and our a, but it's actually going to be multiplied by -2 squared minus 5. We can go ahead and make -2 squared, and so we'll have -27 equal to 4, we'll just put that in front because we're used to seeing it there, 4a minus 5. And then algebraically we can solve by, for instance, adding 5 to both sides. And we get negative 22. And then dividing by 4. And so our negative 5.5 is the a value. That means it is going to vertically stretch from the parent function, but either way, it also gives us the end of our equation. So we now know that the a value is negative 5.5. Of course, for the equation, we want to keep a y, so we're going to keep y equals. Then we'll have our negative 5.5 in there. We're keeping our x because all functions need to have that independent and dependent variable. The h is minus a negative 2, so I'm just going to write plus 2 squared and then minus 5. So this is the equation that will end up having a vertex of negative 2, 5, and it will intercept the point negative 4, negative 27. So that's what you'll end up trying to repeat on the assignment. You're given an h, a k, an x, and a y, and you need to appropriately plug it into the vertex format and then solve. Alright, so that's the end of our notes, and so hopefully each of these pieces is going to help you kind of work through those review pieces of quadratics and polynomials.